All right, let's get started. So last time we were talking about projecting vectors onto subspaces. And we looked at an example, and we saw that if you want to project this vector u onto this subspace W, it ends up amounting to solving this system of linear equations, which you can do. You get a system of equations, and then you solve for C1 and C2. But we noticed that if v1 dot v2, these are vectors that span the subspace that we want to project onto, if v1 and v2 are orthogonal, so the dot product is 0, then you can get that C1 is u dot, if you look at this first equation, you get C1 is u dot v1 over v1 dot v1. And the second equation will tell you that C2 is u dot v2 divided by v2 dot v2. And in general, if v1 through vk are orthogonal to each other, so what that means is if I is not equal to j, then vi dot vj is equal to 0, so they're pairwise orthogonal. And w is the span of v1 through vk. And let's say that you have a vector u in Rn, so these are all vectors in Rn, u which is not in W, then the projection of u onto the vector onto the subspace W is going to equal u dot v1 over v1 dot v1 plus dot 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 plus u dot vk over vk dot vk. Okay? Or this can be written as the sum, using the summation notation, summation from I equals 1 to k of u dot vi over vi dot vi. And I just want to remind you that each of these are scalars, and they're being multiplied by the vector vi. Okay? And in particular, if, in addition, each vi has unit length, so each vi is a unit vector, then the projection of u onto w, well, if vi is a unit vector, how does this simplify? What's vi dot vi? If vi is a unit vector, it's equal to 1, right? Because, how does that work? Because if vi is a unit vector, what that means is that the magnitude of vi is 1. 1 is the magnitude of vi, but the magnitude of vi is the square root of vi dot vi. And so if 1 is the square root of vi dot vi, that implies that vi dot vi is equal to 1. And this is, and also if vi dot vi is equal to 1, that implies that the magnitude of vi is 1. So there's a bunch of ways of thinking about unit vectors. There are vectors where the length is 1, and that's the same as saying that the dot product of vi with itself is equal to 1. Okay. Well, in that case, then this denominator will be 1. And so it actually simplifies a little bit more. It would be the sum from I equals 1 to k of u dot vi. Okay? And now we want to introduce some terminology we would say that a set V1 through Vk is called orthogonal if each of the vectors are orthogonal to each other, so pairwise orthogonal. If whenever I is not equal to j, the dot product of vi with vj is equal to 0. And we say that a set, okay, instead of just repeating myself, oops. We say that the set is orthonormal if it is orthogonal. Okay, we just went over what that means. And each of the vectors is a unit vector, and each vi is a unit vector. Okay, and we say that, okay, a subspace of, well, if W is a subspace of Rn, then a basis I guess it's not really a new definition, but a basis that is orthonormal is called an orthonormal basis. And similarly, if you just have a basis which is orthogonal, then we would call it an orthogonal basis. So we see that clearly from a computational perspective, an orthonormal basis is good because it simplifies the computation, right? It simplifies the computation a lot. And so the question is, how do we produce an orthonormal basis for W if we're given a basis that's not orthonormal? Given a basis for W that is not orthonormal. And the answer is given by something called the Gram-Schmidt procedure, or Gram-Schmidt process. And that's what we'll discuss in this video. And actually, even though there's kind of a fancy name for it, it's really not that complicated. We actually have basically seen the idea. The idea is to use projections. So for instance, let's say that you have, let's just look at R2. So let's say that you have one vector which is like this. So let's say this is our V1. And let's say that you have another vector which is like this, which is V2. Well, right now, the set V1, V2 is not an orthonormal basis. It's not even orthogonal, right? But it is a basis for R2. So how can we change, what can we do with V2 to get a vector that's orthogonal to V1? Well, hopefully, I mean, we know what the answer is. You project V2 onto this line. You take this line and you project V2 onto this line. And so you're going to get this vector. You get a 90-degree angle, and you get this vector here. And that vector is orthogonal to, wait, this isn't supposed to be 90 degrees. It's an orthogonal, let me make it, there we go, 90 degrees, orthogonal to V1. So let's rename V1 by W1. W1 through WK is going to be our orthonormal basis. Well, let's make it orthogonal first. So we want, what we're looking for is an orthogonal basis, W1 through WK. So we would make W1 equal to V1. We just keep the first vector as it is, but we want this vector to be our W2, so it'll be orthogonal to W1, and W2, let's just remind ourselves, is V2 minus the projection of V2 onto V1, which is V1 dot V2 over V2 dot V2 V1. No, it is, let's see here. No, it's not. It's, hold on, getting the formula mixed up. It is V2 dot V1, well, that's the same as V1 dot V2 divided by V2 dot V2, right? Hold on, no, it's V1 dot V1. Is that what I... Right, because the projection of U onto V is U dot V over V dot VV. Somehow that's easier to remember than when you have V1. So my U is my V2 and my V is my V1. I think that's why I'm getting mixed up. Okay, so that's W2. Well, and this is what you would do for R2, right? Your W1, W2 is now W1, W2 is an orthogonal basis for R2. What if you wanted to make it orthonormal? Well, what you want to do is you want to make each of these vectors unit length. So to make a vector unit length, you can scale it. You can scale each vector by dividing by its length. So W1 divided by the magnitude of W1, comma W2 divided by the magnitude of W2, this is an orthonormal basis for R2. Okay, if you want, you can give these names, right? You could call, I don't know, you could call this vector like x1, and you call this vector x2. So your x1, x2 is an orthonormal basis for R2, not just orthogonal. All right. So, and we can do the same thing for R3. Okay, let's just say we have R3, and we have some basis V1, V2, and V3. So we start off with the basis for R3. Then what we can do is we can first project V2 onto V1. Well, we keep V1 the same, so W1 is equal to V1, and then we just use the same formula. W2 is going to be V2 minus the projection of V2 onto V1, which is V2 dot V1 over V1 dot V1 V1. And then what you're going to get is you're going to get let's just draw another picture with the same V3. And you have this V1, which is W1. But now you replaced V2 by a W2, which is orthogonal to W1. So W1, W2 is an orthonormal basis for this subspace, this plane that contains W1 and W2. And now you want to project V3 onto this plane, right? You want to project V3 onto this plane, and then take this vector here. And we saw that that's going to be, so let's call this plane, I don't know, should we call this plane W? Okay, fine, let's call this plane W. Then we want our W3 to be V3 minus the projection of W3 onto this plane W. Which, let's just remember, that's going to be the projection of V3. The projection of V3 onto W is going to be V3 dot W1 over W1 dot W1 W1 plus V3 dot W2 over W2 dot W2 W2. Where we used, let's just remind ourselves that that's W1 and W2. And we just proceed with this formula, with this procedure. If you had Rn, right? So in the case of Rn, if W is a subspace of Rn, and you have a basis V1 through Vk, a basis for W, then we can get an orthogonal basis W1 through Wk by these formulas. You just use these formulas, and then you just, for Wi, it would be Vi minus the projection of Vi onto the span of V1 through Vi minus 1. And then that would be Vi minus, what would the formula be? Vi dot W1 over W1 dot W1 W1 plus plus Vi dot Wi minus 1 over Wi minus 1 dot Wi minus 1 Wi minus 1. Does that make sense? We're just using the formula for the projection. This thing in parentheses is just the projection of Vi onto the span of, well, it's the span of W1 through Wi minus 1, and that's the same as, so note that the span of V1 through Vi minus 1 is equal to the span of W1 through Wi minus 1. Right? Because when we formed our W2 using V1 and V2, we just took a linear combination of V1 and V2. We didn't change the plane. Right? So if you look, if you compare this picture of R3, you have this span of V1 and V2 is this plane. It's the same as the span of W1 and W2. all you did was you just changed the v2 to vector w2 so that w1 and w2 are orthogonal. So that's an orthogonal basis for w. Yeah, I really shouldn't have called. See, I mixed up, not mixed up, but I used the w in two different ways here. So in this example, I have a basis v1, v2, v3, a basis for w equals r3. Okay, so maybe I'll call, instead of this w, let's call this like w prime. This is w prime, to indicate that's not the w in this w. Okay. And then that's an orthogonal basis. And then to produce an orthonormal basis, just replace each wi by wi divided by its length. And then that will give you a unit vector. But it's not going to change the orthogonality. So that's the Gram-Schmidt procedure. It really is just based on using projections over and over and over again. So let's go back to the example before, where you had these vectors u and w is the span of this, and you want to project u onto w. Well, we already found the answer. We found that the answer is going to be that. But we can do the same problem. So let's redo the problem. Do the example above using an orthonormal basis for w. So in the previous example, w was the span of, okay, I don't have this written down, 1, 0, 0, and 2, 2, 1. Okay. So right now we have a v1 and a v2. And this is not an orthogonal basis, because if you take the dot product of v1 and v2, you actually get 2, which is not 0. So first, let's find an orthonormal basis for w. Again, what we want to do is we want to find an orthogonal basis first, and then once you find the orthogonal basis, then you scale everything down to get an orthonormal basis. Well, this is pretty simple. Our w1 is just going to be the same as v1. And w2 is v2 minus the projection of v2 onto w1. So it's going to be like this. Okay. So that's going to be an orthogonal basis for w, the set w1, w2. And what do we get for w2? w2 is going to be v2, that's 2, 2, 1, minus v2 dot v1. That's the same as v2 dot v1. That's going to be 2 divided by v1 dot v1 is going to be 1. And w1 is just 1, 0, 0. So then you're going to get 2, 2, 1 minus 2, 0, 0. And that's going to be 0, 2, 1. So that's w2. So we see that w is the span of 1, 0, 0 and 0, 2, 1. And in fact, you can check that these are orthogonal to each other. But this is not a orthonormal basis, because the second vector is not unit length. What is the length of 0, 2, 1? So if this is W1, that's W2, and the magnitude of W2 is the square root of 0 squared plus 2 squared plus 1 squared, and that's the square root of 5. Right? And so an orthonormal basis for W is 1, 0, 0, 1 over root 5, 0, 2, 1. So let's call these vectors x1, x2. Now we want to project U onto W, and that's the same as we found that that's going to be U dot x1 plus U dot x2 right? Because x1, x2 is orthonormal. Oops, I spelled it wrong. Orthonormal. And what was the vector U again? Okay, it was it 1, 1, 1? No, it was 1, 2, 3. Let's just write that down so I don't forget. U was 1, 2, 3. Well, so you get 1, 2, 3 dot 1, 0, 0. That's 1 x1 plus U dot x2 is going to be 7 over root 5 1, 2, 3. Something about this is a bit fishy. Do I get the same answer as before? Nope. What did I do wrong? Okay. Oh wait, it's 7/5. Sorry, oh, I messed this up. This should be x2. Right? I used the wrong vector. Okay. This, and then x2 is 1 over root 5, 0, 2, 1. There we go. So this is equal to 1, 0, 0 plus 7/5, 0, 2, 1. And this is in fact equal to 1, 14/5, 7/5. And this is the same as the answer we got above. Good. Yes. Okay, you just have to be careful with the vectors because, you know, there's a bunch of vectors going on. All right, so this video, we did the Gram-Schmidt process. We saw how to produce, if you're given a basis for any subspace of Rn, you're able to use projections to find an orthonormal basis for the same space, and that simplifies the computations a lot when we're projecting a vector onto another vector. And when you have an orthonormal basis, we'll see that it simplifies lots of computations. It really helps to use an orthonormal basis. I mean, it's like the same reason why, you know, for R3, you would want to use E1, E2, E3. I mean, in many cases, that's a good basis because it makes things simple. So a typical example, I guess the prototypical example, I should have said this before, of an orthonormal basis. Well, for Rn, it's just the standard basis, E1 through En, right? These are unit vectors and they're orthogonal to each other. And notice that if V is a vector in Rn, V is just V dot E1 plus dot 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 plus V dot V dot En. Right? In other words, it's the sum from I equals 1 to n of V dot Ei. And in general, this is the last thing I'll say, if W1 through WK is an orthonormal basis, I keep spelling this wrong, orthonormal basis for a subspace W, then any V in W is equal to V equals the sum from I equals 1 to K of V dot Wi. And the reason for that, well, we use the same strategy that we've seen before. We know that V is a linear combination, so it's like C1 V1 plus dot 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 plus CK WK. And now if you take the dot product, so suppose that V has this form and we want to solve for the CIs, then if you take the dot product with V and Wi, you're going to get C1 W1 plus dot 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 plus CK WK dot Wi. And now when you use the distributive property, this is going to be C1 W1 dot Wi plus dot 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 plus, and then you're going to get a CI Wi dot Wi, and then plus dot 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 plus CK WK dot Wi. But since these Wi's are orthogonal to each other, everything, you just get 0, and so the only thing left is going to be CI dot Wi dot Wi. But now we use the fact that this basis is orthonormal, Wi dot Wi is equal to 1, and say this is equal to CI. And so we get that the CI is equal to V dot Wi, and that's where this formula comes from. Okay? So that's one thing that's used all the time in linear algebra. Right? We don't actually need to solve a system of equations. Remember that before, if you have a basis for a subspace and you have a vector in the subspace and you want to write that vector as a linear combination of the basis vectors, you need to actually solve a system of equations. But here we have a very simple solution. Okay, so that's what I want to say about an orthonormal basis. We saw how to construct an orthonormal basis, and so every subspace of Rn has an orthonormal basis. Right? Every subspace of Rn has an orthonormal basis because we know that every subspace of Rn has a basis. Okay, do you remember the method for proving that? You just take a vector in your subspace, and then if that vector doesn't span the subspace, you can just take another vector that's not in the span, and then you take the span of those two vectors, and then you iterate until you get a basis for the subspace. And then once you get a basis for a subspace, we showed in this video how to produce an orthonormal basis, and that shows that every basis for Rn, every subspace of Rn has an orthonormal basis. And in the next video, maybe not the next video, but in a future video, we'll take a look at orthogonal matrices, which is a matrix that you get by taking the columns to be orthonormal vectors. Okay, thanks for watching.